What if a building could feel stress, heal damage, harvest energy, clean its own air, and report its health in real time? In this project, we'll explore how graphene, metamaterials, and AI could turn infrastructure into living systems. We've moved from autonomous AI and spatial environments into bio-AI, robotics, swarms, and advanced materials. Project 22 brings those threads into architecture, where buildings become intelligent infrastructure, sensing conditions, adapting in real time, repairing damage, producing energy, and responding to climate. When we say a building behaves like a living system, we mean intelligence is distributed through the physical asset. The facade senses heat, light, wind, and occupancy, like skin. Sensors and data networks act like nerves, carrying signals to AI models that decide how the building should respond. Energy systems become a metabolism, balancing generation, storage, and demand. Advanced materials add the crucial leap. Coatings, graphene composites, and self-healing structures can react physically, not just send alerts. The asset stops being passive infrastructure. It becomes an adaptive platform that learns, protects itself, and improves over time. A living building is not one invention. It is a stack. The structure becomes stronger and more conductive through graphene composites. The envelope uses metamaterials to shape heat, light, sound, and signals. Coatings create a responsive skin that can sense damage, resist corrosion, and help repair small cracks. Sensors and edge devices listen continuously. Then the digital twin turns those signals into decisions, adjust systems, flag risks, schedule maintenance, and optimize energy use. The core idea is feedback. Materials sense the world, AI interprets it, and the building responds. The material stack brings together four major capabilities. Graphene composites add strength, conductivity, and sensing pathways to ordinary building materials, from panels to membranes and cables. Metamaterials shape structure at the microscale, so heat, sound, vibration, or light can be redirected instead of simply resisted. Self-healing concretes and polymers reduce maintenance by closing small cracks before they become failures. Advanced coatings turn surfaces into active systems, filtering air, shedding water, resisting corrosion, or adapting thermally. For founders, the opportunity is not one miracle material. It is integration into manufacturable building products. For a living building, awareness has to be continuous. Structural sensors listen for strain, vibration, deformation, corrosion, and early crack growth. Environmental sensors track air quality, temperature, moisture, light, sound, particles, and occupancy. Fiber optics can carry sensing through long spans and foundations. Graphene layers add high sensitivity detection for stress, pressure, gases, and tiny material changes. Computer vision extends perception to facades, elevators, thermal leaks, and emergencies. The value is not any single device. It is the connected data stream that lets the building diagnose conditions and respond intelligently. Cloud intelligence is useful, but a living building cannot wait for every decision to travel outside. TinyML puts small models directly into sensors and embedded devices, so vibration, leaks, heat, sound, and occupancy patterns can be interpreted immediately. The building edge server then combines those local signals into broader safety, comfort, and energy decisions. Only events, summaries, or model updates need to move to the cloud or digital twin. That reduces latency, saves power, protects privacy, and keeps essential functions running when networks fail. The digital twin becomes the building's live operational brain. It combines sensor readings, energy models, structural simulations, occupancy movement, air quality, and maintenance history into one evolving model. That model tells teams what is happening now, and more importantly, what is likely to happen next. AI can flag degrading materials, predict equipment failure, test ventilation or load changes, and compare options before anyone acts in the real building. At portfolio scale, every asset becomes measurable, comparable, and easier to optimize for cost, safety, comfort, and carbon. Put together, the living building works as a closed-loop intelligence system. First, it senses. Embedded materials and sensors capture strain, heat, vibration, moisture, air quality, light, sound, and early damage signs. Then it thinks. Edge AI classifies patterns, predicts risk, and chooses better comfort, energy, and safety settings. Next, it responds physically through HVAC, adaptive facades, coatings, panels, energy systems, or repair mechanisms. Finally, it learns. The digital twin compares actions with outcomes, updates its models, and improves future maintenance, performance forecasts, and emergency response. Structural resilience changes when a building can sense damage as it forms, not years later during inspection. Tiny cracks create acoustic signatures, strain changes, and moisture patterns that embedded sensors can detect early. From there, the response becomes targeted. Self-healing concrete or capsule-based polymers seal small defects, while AI decides whether loads should be redistributed, a beam reinforced, or a drone inspection dispatched. After an earthquake, flood, fire, or wind event, the building can map stress, classify risk, and generate an evidence trail for engineers and insurers. The goal is not immortality. It is faster diagnosis, smaller repairs, and safer recovery. Now shift from resilience to energy. The building envelope becomes an active system, not a passive shell. Roofs and glass can generate solar power. Floors can convert footsteps into small electrical gains. Facades can use temperature differences, coatings, and metamaterials to redirect heat, reflect summer sun, or hold warmth in winter. The real value appears when these functions connect. Energy is stored locally, shared through microgrids, and adjusted as weather changes. In that model, a building becomes a climate-responsive participant in the city's energy network. Adaptive materials also change the human experience inside the building. Acoustic metamaterials can absorb noise, redirect speech, and create quiet zones without rebuilding a room. Air systems become equally responsive. Smart membranes, catalytic coatings, and sensor-driven ventilation reduce particulates, pathogens, carbon dioxide, and odors as conditions change. The same intelligence can tune light, temperature, humidity, and sound for focus, recovery, collaboration, or care. This extends ambient AI rooms into the whole building. Walls, filters, surfaces, and controls working together to support comfort, health, and attention. When adaptive buildings connect, intelligence stops being local and becomes urban. One structure can warn others about wind loads, vibration, heat, pollution, or seismic signals. Together, they form a resilience layer that detects stress before it becomes failure. The same network can balance energy across a district, moving power from generation and storage to where demand is rising. Over time, the city starts to behave less like a collection of assets and more like a living system, sensing conditions, circulating resources, coordinating response, and continuously improving performance. By 2050, the biggest opportunity may not be a single green building product. It may be the operating system for buildings themselves. Founders can enter at different layers: advanced materials, sensor networks, AI twins, adaptive facades, building health analytics, insurance, energy, and resilience finance. The key question is where your idea sits between deep technical advantage and scalable platform value. A coating may start as material science, but become a data and services business. An AI twin may start as software, but reshape maintenance, safety, and capital markets. The winners turn buildings from depreciating assets into learning infrastructure. The core lesson is that buildings can become living systems. Smart materials repair damage, sensors detect change, TinyML makes local decisions, and digital twins help the whole system learn. That closed loop can improve safety, comfort, cost, and energy performance. Next, the same logic moves smaller and wider into intelligent particles, programmable energy, and climate repair.